Hi, and welcome to this quick look at how a halogen carrier works. So we'll use AlCl3 as our example, and we'll also have a look at how a Friedel-Crafts alkylation exam question might present itself to you. So the first thing to remember, well actually you don't need to remember it for the OCR specification, but if you're required to remember this for other A-level specifications such as AQA for example, AlCl3, although it's a compound between a metal and a non-metal, it can exist in covalent form because aluminium is quite close to the boundary on the periodic table between metals and non-metals, so exhibits some non-metallic behavior, including some covalent bonding in certain conditions. So if we start with our aluminium atom, I'm not putting any outer shell electrons just yet, and we assume that there's 3 covalent bonds to 3 chlorine atoms to make AlCl3. What you'll notice is the aluminium atom only has 6 electrons, that's right, in its outer shell. So it needs 2 more to complete its octet. So it has 3 outer shell electrons of its own because of its position in group 3 of the periodic table. So this means the aluminium atom is quite reactive and it wants to get 2 more electrons to complete that octet. So a chlorine molecule can provide these 2 electrons. So if we put a chlorine molecule next to our AlCl3, you can see that there's lone pairs on each of the chlorine atoms. Now one of those gets drawn in by the aluminium, and this forms a data covalent bond, but in doing so, it also breaks the bond between the chlorine and the other chlorine atom. So that in effect makes this species, AlCl4-, and it also releases Cl+, which is an ion that can now go and attack a benzene ring, and it can behave as an electrophile. So let's have a look at this in terms of Friedel-Crafts alkylation. So a chlorine-containing hydrocarbon molecule can also provide the remaining 2 electrons. So if we take chloroethane, for example, and we highlight the lone pairs on the chlorine, they can actually also move on to the aluminium, and you can end up breaking the carbon to chlorine bond. So what happens is the lone pair on the Cl atom forms a data covalent bond with aluminium, and the CCl bond in CH3Cl2 CH2Cl breaks to form AlCl4- and the CH3CH2+ electrophile. Now this carbocation, or CH3CH2+ is fine to write it like that, can actually go on to react with benzene. So we're going to look at an exam question to see how this might present itself. So it's from an AQA paper, and first thing they want you to do is identify 2 other substances needed to carry out the reaction in step 1. So if we clear the labels for the 2 compounds, ethyl benzene and phenylethene, we can now just put in what 2 things need to happen. So the ethene needs to be changed into chloroethane by reacting with HCl. This will chlorinate it on one of the 2 carbons. And then that chloroethane can go on to react with AlCl3, like we just talked about, to make the CH2CH3+ electrophile. Now, I just want to point out here that it's good practice to put the positive charge on the carbon that has the positive charge on it. So in other words, don't put it over here next to the CH3, put it over here next to the carbon on the CH2, because it's that carbon that actually ends up here. So you'll notice where I'm highlighting it, there's a bond. So therefore that's where the positive charge should be on the electrophile. It should be on the atom that forms the bond with the benzene ring. So the 2 substances that we're looking for are HCl and AlCl3. Now, they've said write an equation for the reaction of these 2 substances with ethene. So that bit there, these 2 substances with ethene, suggests that there are actually 3 things in the reactant side of my equation. So you have your ethene, your HCl, and your AlCl3. That makes your AlCl4- and your reactive intermediate, CH3CH2+. So you can see the way they've done it in the question. They've put the positive charge by this carbon. They've not put it over here. So I'm following their lead. So just to reiterate how we process this, you must have 3 reactants and the CH2CH3 plus is one of the products. So the next part is to name and outline a mechanism for the reaction of this intermediate with benzene in step 1. So just reminding ourselves what step 1 looks like. The mechanism is obviously electrophilic substitution, and the mechanism will look something like that. So I'm just going to put the marks in the mechanism where they would be awarded. So there's 4 marks on offer. The first mark is obviously for the correct name. The second mark is for the curly arrow coming out of the circle within the hexagon and the positive sign on the carbon of the CH2 part of the electrophile, like we talked about a moment ago. So what I mean by that is the positive charge. It doesn't have to have a circle around the plus sign. I just put it there because that's the way I prefer to do it. It sits on this carbon where my highlighter is. Now the third mark comes from the curly arrow from the CH bond, pointing into the open part of the delocalized pi system. So the curly arrow starts at the CH bond and it points into the open part of the partially delocalized pi system, which is this U shape with a positive sign inside it. The fourth mark comes from the correct structure of the intermediate. So what they mean here is mostly the U shape. It extends all the way up to these 2 carbons here. So if you imagine a little line where I'm toggling my highlighter here, that's how far up the U shape goes. And it needs to be, the open part of it needs to be in line with the site of substitution where I'm leaving my highlighter at the moment. Okay, so hopefully this has been a useful look at an applied example of Friedel-Crafts acylation, and also a little bit of background, whether your particular specification needs it or not, on how a halogen carrier works. As always, thanks for listening. Until next time, see you soon.